Hey, I did get up at 3:30 to make it to Raleigh by 7. It was not a leisure day. Okay, so this is the application of the concept behind equilibrium and Ka. So let's quickly review these, and then if you would take a minute first to talk to your partner. Tomorrow we'll go back to like general seating. I had to do this because I had a setup. So talk to a partner first for about a minute on these 4. You have to open your mouth. All right, come back to me. 3, 2, 1. All right. Large K associated with what kinds of? Well, first of all, we see the. No, sorry, I didn't say Ka. I do want to say Ka. So large Ka value means what? Strong acid, right? So we actually don't even have Ka values for the strongest acids. So I provided you a list of, just because in the back of your textbook you have all these K values, Kas, Kbs, Kws, every K known to man, but I thought this would be easier to work with. So look at this list. Do you see at the very top, there's a blank spot of Kas. It doesn't have a Ka. Why do those specifically not have Kas? Those are all of ours. Well, I think there's 7 here. 1, 2, 3, 4, 5, 6, 7. Yeah, because they also, not everybody includes chloric acid as a strong acid. We don't, but it is strong-ish, so they'd include here. So there's a 5. Is there 6 or are there 7 strong acids? But we're going to stick with our 6 for now because that's what we want. So there are no Kas here because it's infinitesimally large. It's so large because it makes all products and leaving over no reactant. So the Ka value is associated with the strength of the acid. So if it's a strong acid, it's going to have a large Ka value. If it's a weak acid, it's going to have a low Ka value. Can K be less than 0? Can K be negative? No. Okay, so K can never be negative. It's between 0 and whatever, infinity. But if it's less than 1, it's going to be a small K value, which would be indicative of a weak acid. So I'm sticking with K for now. We'll talk about Kds more today. What about the strength of its conjugate? And so what I mean by that is our generic way of writing is HA plus water equilibrates or dissociates to make what? So hydronium plus 1, okay, and A minus. So who's the conjugate? The what? The A minus. So this is the acid, and this is its conjugate base, because this is the acid conjugate base pair, because they are only different by what? Just 1 proton, or 1 H plus. That's really the main difference here. So if this was a weak acid, this would be a what conjugate base? Strong conjugate base. And if this were a strong acid, this would be a weak conjugate base. And basically what that means is strong acids make ions that will not reverse. So strong acids are going to push to make products, and this A has no attraction for the H plus here, so it won't take it back. It won't act basic, it just isn't strong enough. So it's more favorable to go in the forward direction. But a weak acid makes a stronger conjugate base, which means it will act basic, which what do bases do? Say what? So what are they? So the definition of like a Bronsted base. Whoa, bad acids are donors. This is an acceptor, okay? So if something's acting basic, it's just accepting an H plus back. So this base, if it's a strong conjugate base, is acting basic and it will accept this H plus back, meaning it will reverse the reaction, making much, much, much more weak acid, which we know is true because weak acids don't appreciably dissociate. They don't appreciably make many ions. So that's really what's happening is as soon as it ionizes, that base is like, give me that H plus back, swoosh, goes back the other way. So that's why we have a lot of a lot of the original weak acid and very little of the two products. And then if you have a strong acid, what's the concentration of H plus in the solution, or hydronium? High or low? High. You're making a lot of product of the H plus because it's strong and it's making all of the H plus dissociate. And if you have a weak acid, you have a low amount of H plus because you're not allowing very much of it to dissociate, which is why a lot of times you're neglecting X because there's not an appreciable amount of dissociate that's formed. And then this was the amazing pictures that I was drawing yesterday. The bonds, you had like sulfuric acid, sulfate with some H's attached to it. If you had a strong acid, what's the strength of the bond that attaches H to the overall acid structure? Weak. So that weakened bond allows for water to come by with its polar little butt and pull that H plus right off. And so if you have a weak acid, what's the strength? There's a strong bond, and that bond is not like called up, it's not necessarily, well actually, absolutely it's not called a hydrogen bond. A hydrogen bond is what's occurring between a molecule and another molecule. There's like this intermolecular force called hydrogen bonding. This bond is simply like, if you have a group like acetate, sulfate, phosphate, any H really with O's in it, oxyacids, and there's a bond here. That bond there is the one I'm talking about. It's the one that holds this acidic H, acidic hydrogen to the overall structure. So this bond, if it's strong, would this be a weak or strong acid? If this bond is strong. It's a weak acid because it doesn't allow the H plus to dissociate. So really that just all goes back to what's the definition of strong. 100% dissociation or not. Okay, so we kind of went through the strong stuff and the weak stuff at the same time, so I'm going to skip this section. All right, take another minute and talk about these three. I think you can see all those.
So it's like the strength of the acid. So if it has a high percentage, or good. Yeah. Like we see like 5% ionization, weak bond, strong acid, increased concentration of blood. Exactly. Which is stronger?
Here and right things. All right, come back. So this last question we may not be able to do yet because there's one slide you didn't get to on your video yesterday. So you went through this percent ionization. When you went through the calculation part of determining percent ionization, what was this exactly the same as that we had done before? The 5% rule. That's really it. So if we say we dissociate, we make X amount of H plus, that X is divided by the initial concentration of the acid or base, and that gives us just the percent that's ionized. So we always say if it's less than 5%, we're able to neglect X, which most of the time we're going to be able to do that. So which scenario gave you a higher percent ionization? A more dilute concentration, right? It was weird because you didn't really necessarily expect that, but smaller changes, or even any change that's made to a smaller concentration, makes a bigger difference. Like a drop in the ocean makes no difference, but a drop in a milliliter of water makes a big difference. So that's the percentage breakdown, kind of, it works the same way. So a more dilute concentration of the weak acid is going to cause higher percent ionization, which is where we get into trouble, because if we have like a 0.0001 molar acid and we run through, ice box and we get to the X, and then we do our percent ionization, or the 5% rule, it might be 10%. So we've neglected, oops, we weren't supposed to, we'd have to go back and do quadratic equation or solver, calculator, okay? But with that, we start to see that very, very rarely, but you did see it on your problem set question like 5 maybe, one of those questions. Okay, and this is all based on the Le Chatelier's rule, Le Chat's principle. Basically, as you have your generic equation again, this is liquid. We have water, right? And all these aqueous species. Water is irrelevant in all of our equilibrium expressions, so it's not going to increase or it's not going to cause any changes in K. So if you dilute the acid, you're making this dilute, you are also going to be, you're in a higher amount of water, liquid water. You're also making diluted concentrations of 2 ions versus just 1 ion. So it's almost like you're doubly decreasing the concentrations of the products. So you have this nice balance of equilibrium. If you decrease the concentration of the products 2-fold versus just 1-fold because of the ratio of the ions to ions, it's going to make more of an impact on the products. So the equilibrium is going to continue to push forward, like Q is approaching K. It's going to continue to push forward, which is the shift right, like Le Chatelier's principle indicates. So as we do that, we get more product formed than we thought was going to form, which is why we say it has a higher percent ionization, because you're just naturally making more X, making more hydronium. Okay, so between these, which is stronger? Name that. Perchloric acid. Okay, so perchloric has, not C, Cl. I'm going to kind of draw it like this just for clarity what we're looking at here. There's one H attached to it. There are some like double bonds. I'm not going to go through the formal loose dot structure right now. And over here we got just, okay. All right, so here's our basic 2 structures of these 2 acids. So why is this one considered stronger? What are you trying to indicate to me about something within the structure? The oxygen what? Say again? I heard oxygens. I mean, that's one side of the story.
Makes the electron polar since the electrons are more towards the oxygens.
Okay, so the electrons are more towards the oxygens. Everybody do this. Okay, your left hand, like a little L shape, look at the periodic table. Okay, your fingers are arrows pointing up a group and across the period. So the farthest away from you, the corner of your hand, is the most electronegative elements in the periodic table. Helium doesn't want electrons. That's just, they're noble gases. But fluorine is very, very electronegative. Oxygen's right next to it. It's very electronegative. Just which, in the case of bonding, that just means that electrons in a covalent bond move towards oxygen, towards oxygen, towards oxygen, towards oxygen, towards oxygen. So it's still shared. There's 2 electrons in the bond, but they're just pushed one direction. So what you're seeing here is that there's this large field of an electronegative space. So it's just not just pulling electrons towards oxygen. It's like, bye Felicia, like water come in here, sweeps it away. It's just super, super electron dense. So the electron density is super high, so it's going to cause a very, very polar partial negative area over here and leave this very, very partial positive. And so which part of water attracts the H? The oxygen has the negative, has the electrons on it, so it'll bond to that extra H here. This doesn't have quite the same difference in electron density, so that's why this bond is considered what? Stronger or weaker than that bond? Stronger. So you're really going to have to ask water to come in an army to really pull this one off, and it only happen 1% of the time, which is why it's a weak acid, because it doesn't happen very frequently. This is going to happen 100% of the time, because there's no way that hydrogen's going to win the electron war. Okay, so what you're seeing is like a combination between conceptual, bonding, and like what does it mean in terms of the structure, and then also equilibrium, which is why I kind of saved this one, because it's just a little bit more brain power. And then, okay, we'll talk about this one later. Okay, this is kind of what we just went over. Just give me a thumbs up if you get this. So just trends that you should be familiar with multiple choice specifically, because they're easy questions to get right. So is hydrofluoric acid weak or strong? Hydrochloric. It's the only halogen, or yeah, really the only halogen group that is not a strong acid. So with it's HF here, right? So we have H plus and F minus. Is this a strong or weak conjugate base? Strong conjugate base. It's going to take the waters or the hydronium's H back. Well, let me write this out. So we know that this will occur to a small extent because it is weak acid, but what we're going to see is this H plus will bounce back to F quite frequently because it's a strong conjugate base. And as that bounces back, you get a 99% reverse reaction, which is why we see in solution a lot of HF, but we see very, very, very few F minus. And then nitric acid is going to do something different, like what? What's its arrow look like? Just a forward direction. So you don't always have to write it in water, but because they have an aqueous solution, I'm going to try to make sure I do that more frequently than not. You get 100% ionization as the H gets donated, because this is a strong acid. As the H gets donated, you make nitrate. So in the end, what are the species present in solution? In the end, nitrate and hydronium. You actually don't have any nitric acid at all. It's a lie on the bottle. It's not actually there. The oxidation number, or the oxyacids, kind of come into play again. So you should know the grouping. It's like sulfate versus sulfite. This is a stronger acid. This is the weaker acid because it's got more oxygen, so that electron density rule applies again. And then kind of the same thing here, nitrite versus nitrate. More oxygens, greater electron density, stronger acid. So it's an easy, like when you're in the same theme, like I could go higher or lower in oxygens, as long as I'm looking at the same generic poly, then I can make that comparison. And then this question 3, if you want to pull out that now to look at the NMSI. This requires you to read and kind of think about Ka values. What the heck is this ion? Like, where did it come from? And how could it act basic? Because it asks for you to arrange it in this in increasing strength. I think I did increasing strength. Yeah, I did increasing strength, so that's how we're going to handle it. So this was an example, another example, so I'll come back to this in a second. But what you should realize is that a cation, as it has a positive charge, cations are more willing to give up H pluses because pluses and pluses, right, cations and other things with positive charge, they don't really have an attraction. So they're willing to give up an H plus pretty easily compared to a neutral atom or a neutral molecule. But then when you get to an anion, anions have negative charges. So if you're trying to give up an H plus, they fight back because the negative and the positive, even though, you know, it still might be willing to give up the H plus, it's just not as willing. So it's a lower K value because it's not going to, the attraction here kind of allows for the H plus to stay in place more frequently. So that's how we compare just ions across the board. So in addition to that thought, we also had to look at some K values for these down here. So I'm going to tell you our thought process. So we're looking at all these. We noticed there are 2 just monatomic ions. Well, if we're looking at acting as a base, what would these 2 become if they act like a base? Acids, right? Which would be what acids? So HCl, so the Cl would become HCl, and the H, or the F minus would become HF. So now immediately I already know what kind of conjugate bases they are based on who they formed. So Cl is the what conjugate base? Is it strong or weak? It's a weak conjugate base. Are my abbreviations okay? Okay. So Cl is a weak conjugate base of a strong acid. HCl is a strong acid, so you can interpret that. So that's going to be like our weakest of them all, because do you see, well actually almost, no, that's right. Do we see any other strong acids or conjugates of strong acids? No, because NO or nitrite is going to form nitrous acid, and then CN is going to be cyanic acid, and then we've got water. So if you look back at their acid comparison, you can come to some conclusions, but then we're going to look at Ka values from here. Okay, so HF is the what conjugate, or F minus. F minus is a strong conjugate base of a weak acid because HF is not as strong. So those are going to kind of be our two ends on the range because we've got a really strong acid and like certainly a weak acid. But then we look farther and we see more weak acids here. So that's why we can't just automatically say, okay, fluoride, you're on one of the capped ends because we do have to make a comparison between these. So here we go. I'm going to go in increasing strength of base, or base strength. All right, so in kind of our conclusion so far, who is the weakest base? Say again? So it's not hydrochloric acid because that's not one of our options. So just the chloride ion is going to be the weakest because it's a weak conjugate base from a strong acid. There's no other strong acid counterparts here, so that's how we kind of knew that. Then from there, we see water. Well, what is the K value for water? It's called the ionization constant for water. Okay, so water is kind of a weirdo. It's got its own little KW, 1 times 10 to the negative 14th. Okay, so on your list now your list might vary here from mine, but look at your list and tell me the Ka values for the rest of these. For these three. What's HF? 7.2 times 10 to the what? Negative 14. I have it on this paper. Okay, for nitrous, to the negative 4th, and cyanic. Okay, so from here, and then we have water here. Who is the worst acid? Keep looking. Water. Water is the worst acid. So, because essentially it's amphoteric, so it can act as an acid or a base. So I know we might be concerned about where we're going to plug this in, but it can act as an acid, just it doesn't, it won't be as strong as maybe the other ones. Thanks, we got it from. So let's put water here for now and put amphoteric. What does that mean again? Act as an acid or a base, KCJ. All right, so then who's the next worst acid? Who? Cyanic acid. So that means, oh, hold on. Let me revise this. This is amphoteric, by the way. But what we are going to, I'm doing this before I tell you all this story behind KW. So I'm going to have to tell you this first. KW is equal to KA times KB. So we actually have to revert back to what the Ka, the way the strength of the acid would play out for water. And it's half of, or it's the multiplication of the H plus and the OH minus. So it's actually 1 times 10 to the negative 7th because of the amphoteric nature. You have equal concentrations of H plus and OH minus. We'll get back to this in a second. I'll write Ka here for me. Okay. So you guys just said the next worst acid was cyanic, which what do you mean about its conjugate base then if you say it's the worst acid? It's a pretty strong, I'm going to say strong, but it's a stronger base than many of these others because it's the worst acid. Its Ka value is very low, so weak acids make strong conjugate bases. So we're going to put that on the high end, okay? Way over here, but we're going to use the ion as it was indicated. Okay, keep going. Who would be the next, or who would be sequentially in this place for bases? So, compare these two K values. Who's larger? Who's larger? Hydrochloric. So, shouldn't it be, this is higher, so that, oh no, this makes a weaker base. Sorry, this is next. All right, so this is the, I'm gonna say number 1 on this side, this will be number 2 of the strong conjugate bases, nitrite, and then sequentially kind of moving up, this is a little larger, so it's getting to be a better acid, and better acids are worse bases, so that's why we're kind of falling down this way. So this will be number 3, and I think we've completed our journey now. Because at this point, so we good? Okay. At this point now we can see our Ka value of water is relatively small. I'm going to tell you water is right here just because it's amphoteric. So just we're going to deal with that one later. Okay, so it does take a minute to think about the strong and weak comparisons, especially when you're comparing conjugates. Let's go to KBs. I do want to check a little bit of homework before we do that. Okay, so on homework, this was the last thing from yesterday. Write this down first and then we'll talk. So basically what this is giving you is another variable. Like we can talk about acids making H pluses, but then we don't always talk about, hey, just here's the acid's H plus concentration or hydrogen concentration. A lot of times we talk about the pH of an acid. So we just modify a variable to talk about it in a different way. Like pH, we know the pH scale very well, so it's really natural for us to talk about that. The unnatural thing for us to talk about is pKa, but it's just a mathematical modification to Ka. So just like for a strong acid, where would your pH fall for a strong acid, high or low? Low. Okay, so strong acid, low pH. Is that a direct or an indirect relationship? Say again? Indirect. Good acid, like a high concentration of H plus, low pH. So that's an indirect relationship. So we're going to have that same relationship here because P means to do what mathematically for us? What does P mean for us to do? Negative log, right? So that negative that's here is what's making it inverse. That's how we're getting this opposite effect. So if you have a strong acid, what's your Ka? Strong acid, lots and lots of product. A lot of K. So a large K? Okay. So if we have a strong acid, we're making a lot of product, associating quite well, we have a large Ka value. That's going to inverse when we talk about pKa, the negative log of Ka, which is why we get a smaller pKa. It works the same exactly as pH does. It's just not talking about H plus concentration anymore. It's talking about the Ka. So as long as we know the relationship is negative log and you have the Ka value, you could calculate it, and then vice versa. If you had pKa, antilog is using 10, so 10 caret negative pKa will give you just the Ka. So that's just one more tool in your toolbox. You okay? It's the same relationship though as pH or POH, even with OH concentration, and KBs for bases will work exactly the same way. It's all the same concept. Okay. You guys had 5 on your NMSIs. So we know the normal KW is 1 times 10 to the negative 14th, but this was given to us at 60 degrees Celsius. When is KW 1 times 10 to the negative 14th?
25 degrees Celsius.
25 degrees Celsius, right? Standard conditions. So at 60, we see a larger or smaller K value. Come on, larger or smaller?
Larger.
Larger. I got like 3 people with me. So it's larger than KW at 25 degrees C. So what does that tell you about the direction this equilibrium is shifted? It's shifted in the forward or reverse? Forward, so to the right. It's made more and more ions, which is why I have a larger K value, because it's favoring more products. So you're essentially telling me that this, well, in this scenario, it's favoring products more. Okay, so at this point, all you're looking at is the energy or the thermodynamics of this now. If you have a favoring product situation and you've increased the temperature, where would you place heat? As a what? As a reactant. You'd actually have to say it's endo or exo then. Endo, and that delta H is positive. Ooh. I just tutored somebody on this from Hickory Ridge. We went through this for like an hour. Okay. All right. So basically, if you have more product, you push to the right. Pushing to the right means energy cannot be a product because that's going to push the opposite direction as you heat up. Increasing a reactant will push towards the products. So like a flight attendant now. Okay. Now I want you guys to tell me how you would solve for concentrations of ions. Okay. H plus times OH minus is equal to, and okay, so the KW for 60 was this. So then what do I do? Square root it, because this is making equal concentrations as the ions are made. X and X is amounts. So X is equal to 3-ish times 10 to the negative 7th molar. And these are for both ion concentrations. So how do you compare that value to the value at 25 degrees Celsius? This value is, say again? Yeah, it's higher. The other one is 1 times 10 to the negative 7th. This is 3 times 10 to the negative 7th, so we have a larger value, which makes sense because we have pushed right, so we've shifted right, so we should be making more ions. All right, stand for a stretch break. Go talk to somebody about homework or what maybe you've now had your aha moment for. Raise your hand if you're like, I'm lost. And I need a favor. It's a different person talking. But this is all equally well, there's a lot of extra stuff with that, so that wouldn't be for free. Give a note. Alright, find a seat, find a seat. Okay. Hopefully no one has Snapchatted you already this morning. It is like not even 8 o'clock. All right, so we're going to check this real fast. I'm going to go actually kind of from the bottom and then come here with Drake. That's kind of old. I'm sorry. Okay. Let's start with 5. Cool? Can I start with 5? Okay. So I'm going to try to make this big enough so you guys can see. Make sure. Or should I start with 4? Start with 4? Okay, so hopefully I have like lessons. I'm going to try to finish up KKAs in 10 minutes or less so that we can practice some of the other varieties of questions we have. So we have this, like phenol something, yeah, phenol, and we are looking for the predominant species in solution. Every single time they ask us to dissociate, it is in water. So a lot of times I'll write plus water on all of these dissociation equations, but it may not always be there. That's why this is like a cheap way of doing it. You'll notice that H plus is present. It's not hydronium, but it is hydronium because that is technically what's present. So major species, because it's weak, is going to be the true weak acid, and then water because it's an aqueous solution. We won't have a lot of these because we have such a small Ka value, we don't have very many products. So in efforts to solve this, you're setting up your ice box. So there's our cheap equation with no water in it, but if you have water, just ignore it, it's there. We had our initial concentration of 0.25 molar, and it said solve for the ion concentrations. So if we don't have anything else but Ka, and we have concentration, you can't do anything except utilize X's as your placeholders. So as you dissociate, you subtract from reactants, you produce products in a 1-to-1-to-1 ratio, giving you 0.25 minus X for the equilibrium of the weak acid, and X for the two products. So I'm going to scroll down here because I'm going to show you this in a second. I'm going to scroll down here and to show you the work. So since this is a weak acid, this is the assumption. You have to neglect X. You have to show the process of neglecting X. It's not because it's the right way to do the math. It's because it's the right concept. So when I'm neglecting X, what am I really saying about this acid? It's a weak acid. It's not going to dissociate. There's a very, very, very little change that's occurring to this initial concentration. So what you'll start to see is that they do the equal or approximate symbol. So they'll say, this concentration at equilibrium is approximately equal to what it was initial because there was no significant change in those values. Now these are the answers here, but I solved it down here. So let me scooch. So we have set up our Ka, products over reactants. So there's our H plus or hydronium, phenol ion, and then the phenolic acid. And as we made X and X amounts here, X and X, notice that I neglected X, so I did not include the subtracted X in that denominator. And then set it equal to Ka, and then checking, multiplying the 0.25 up, you get 4.0 times 10 to the negative 11th. And then square rooting the X, you get 6.32 times 10 to the negative 6 molar. This is the X that's applicable to not only H plus, but also the other ion produced. So it's very small, right? So we double check it's neglectable by taking X over what? 0.25, and I got less than 5%, so don't know what it was exactly, but it was less than 5%. Yeah.
Where'd you get that K?
Oh, did you guys have it on your paper? I was in the back of the book. I also have this nice copy now for you, so it was easy. I think I said it probably on the video, but if I didn't, that's why you just have this now. It's right in front of you because I know you're not carrying your books around. So yeah, if you didn't think to look for a Ka value, because they're all published everywhere, I get it. This is the first time we're seeing this, so thank you for asking. If you don't have a K value, Google it, look on the sheet, or look in the back of your textbooks. Okay. All right. So now we have. So if you're writing some of this down now, go for it. I know you guys can set up, but maybe you didn't have something you needed. So once we have the X value, which we now know is H plus, because that's how acids work. They make H plus. There. I did not make that up. This is this here. You can find pH by taking negative log of H plus concentration, and you get 5.2. Is that a pH that's indicative of a weak acid? Yeah, it's getting closer to the 7 to the neutral side, so it is definitely showing weak. And then, why do I have 200 back here? Something about sig figs, right? So in pH, the sig figs exist in the post-decimal area, and I'm thinking it was 0.250. I wrote down 0.250 anyway. Yeah, so 0.250 shows us a 3 sig fig concentration. 3 sig figs get applied in the decimal on pH. So at that point, we have found the pH. We know it's showing weak. And then it said to find ion concentrations, which for us, the small x made 0.250 essentially the same at initial and equilibrium because you subtracted so few ions. The H plus is what X was, as is this 0C6H5 minus. And then it also said to find all ions in solution, which if H plus is present in solution, who's its kind of counterpart that's always present as well? OH minus, so hydroxide. So as a reminder for hydroxide, if you have H plus, you will have hydroxide, and their relationship, that's really tiny. So I'm telling this to you now. This is Kw, so 1.0 times 10 to the negative 14 divided by the concentration of H plus to give you OH minus molar. Yes, ma'am. Yeah, it's tiny. This is Kw over H plus to give you OH minus. All right, take a second and look at the next ones, because if you need a Ka value, you have them in front of you, and chat with your neighbor for a moment to see where you're
But see, I really don't know why. I'm going to keep getting.
Actually, I have the right answer for A, but I can't get the right answer
Let's see. I looked at it like now I'm like, I know how to do it. I did it before and I did it. So you just find solve the same way with but now you have a different initial value, which is the root value now.
Yeah.
So
you always solve.
Yeah.
Yeah.
So set up an ice table. How are they going to see? Now we'll go see 1.5 now. It'd be different. You did the same thing where you would like the so just be like X minus 1.5. Then you take whatever you got for X, since that's your H plus concentration, you just divide it over your initial acid, and it's like 0.5, and then it's about 100.
anything ionic. Basic, a lot of dissociation for acid, just acid. KSP ions. We use dissociation in ion. Don't overthink it. Don't overthink it. Okay, so let's jump to I think 6 was set up differently. Okay, so let's talk about 6 first, because it's set up differently, and if you can set up one, you should be able to take that and apply it to many others. So with 6, we were given different data. We were given hydrobromic acid had a 0.063 molar concentration initially, and its pH was 4.95. So if we are starting off with pH, they're not giving us information directly. They're giving us what indirectly? Yeah, they're secretly giving us H plus concentration. So because we know how to modify pH to get H plus, which is 10 to the negative pH, 10 to the negative 4.5 will give you 1.122 times 10 to the negative-ish molar of H plus. Once we know H plus, our icebox is now essentially complete. I know this is little, but that's because once you set up an icebox for a Ka 10 times, you get you're like, I got this. It's X's and X's. I mean, that's it. So I'm going to make that a little bit bigger for us. because we had our initial concentration given to us, it's huge. Whoa, okay, because we were given our initial concentration and we knew it formed an H plus ion, we knew X now because of pH, which was 1 times 10 to the negative what? Negative fifth. So if we know that X, we also know this X because they're a 1-to-1 ratio. And that means we know this X, which is the subtracted change version of the original weak acid. Since our icebox is really complete, and you plug it in as it pertains to Ka, which will always be set up as products of reactants, which is always hydronium or H plus, its conjugate base over the weak acid. That's our general setup all the time. Those were forming in equal concentrations of 1.1 times 10 to the negative fifth. We knew our change, so we actually have to subtract it. We can't just neglect it. Since we know the change, we are going to calculate. And then we're going to set that equal to, or we're going to solve, and then that will be our Ka value. Yes, ma'am?
So when an acid is a bad product, does it only always donate 1 H plus?
It donates 1 H plus at a time. That is our topic for tomorrow. Okay. Yeah, tomorrow. So it has a sequential as a Ka1, a Ka2, a Ka3, and so we have to do like 3 iceboxes. Okay. But the first one's the appreciable one, so it really doesn't change the pH. So we kind of don't do the last ones if we don't have to. Okay. So if in 7 you struggled, it was very similar to 6. You were given pH, so secretly given H plus concentration. Is this like formic acid or something like that? And your H plus concentration would be 1.99 times 10 to the negative third, which would be your X values. So the weird thing with this one was you actually did not have an initial given. So I just put question mark or like Y right there. But once I found the amount of change, so X plus X plus X, I could plug in that single value in all of these scenarios. But we were given Ka, so we did have enough information to solve for this one unknown variable. So Ka, 1.8 times 10 to the negative 4. Here, X times X over, I just said Y minus X since I didn't know what this initial concentration was. You have to do a little math. So by multiplying out 3.96 times 10 to the negative 6, and then the denominator stays Y minus 1.99 times 10 to the negative third, because that was our X value. So by manipulating, you can see it's nice and just, so legible. You can see everything here. So I kind of just manipulated, pulled the Y out, solving for Y by itself, which if you're a solver person, I can't scroll down anymore, sorry. If you're a solver person, you probably got to this point, you're like, okay, gonna solve for Y. But I do want you to try to show your math, because you shouldn't lose like basic algebra, like this wasn't that long ago. You should get about Y value of approximately 0.024 molar. And that's your initial concentration. That one just set it up just a little different, so I wanted to show you how you would isolate Y. All right, do you guys feel a little bit better? Do you see that there's a lot of similarities to equilibrium, general equilibrium? And it's going to be very similar for KB and then salt hydrolysis next. Okay, you need a sucker for a little sugar boost? Now is the time. Okay, we're going to go through KBs. If you want to pull your notes, I will post this key later, but I wanted to hit the highlights before moving on. So we're going to do some quick reminders of just pH fluctuations again, and then we're going to set these up as KBs, solve for a various number of problems just to make sure we're good, and we'll talk about salt hydrolysis, because it's just applied the same thing but dealing with salts. So we know for strong bases, our pH is generally going to be what? Strong bases pH will be what? High pH, okay? And then for weak bases, the pH will be between what? 7 and probably like 11. It'll be between there, maybe 12. But your higher pHs are likely to be strong between like 12 to 14. So when you're finding pHs and you're looking at the type of problem you're working with, kind of make sure it makes sense. You're not, working with POH or something by accident. So strong bases, what does this forward arrow indicate? complete ionization or dissociation, as we like to interchange those terms a lot. So 100% ionization or dissociation means that if I had 1 molar initially of the strong base, I no longer have it as a strong base itself. I've actually made 1 molar of the metal ion in hydroxide, which, who cares about the metal ion? What am I really concerned about here? Hydroxide ion. So that's why it's so important to recognize first the type of problem you're dealing with. If it's strong, immediately take it to make the the OH minus concentration, and then that would be what you would plug in to find eventually pH. So those are the simple ones you did in honors chem. So as an example, I have sodium hydroxide, so determine the pH of 0.0048 molar sodium hydroxide. Go. And I'm just going to write down all my thoughts. This is not like the level of detail you would necessarily need to write out, but it is your thought process. See what you get. Say again? 11.7. Can you give me the correct significance in that pH? 6.8. Okay. So can I get a second on that? I did not calculate. 11.68. Okay, so we know it's strong. We 100% ionize. We make the OH concentration exactly the same as the original because it's making 1 OH at a time. And then we plug in our concentration into finding pOH. Well, you don't actually have to find or solve for pOH. You can just straight modify the equation for pH. So because pH plus pOH is equal to 14, we did 14 minus pOH to give us initially, or just the pH. But pOH is negative log of OH concentration. So as we plug that in, we can just take one big calculation and solve for pH. Does this value make sense for a strong base? It's basic, right? Definitely basic, but it's kind of getting to be that mid-range. Why is it mid-range? Why is it not like 14? Yeah, that's a pretty dang small concentration. 4.8 times 10 to the negative third is very dilute, so that's why it's kind of going down towards the 7 side of things. Okay, and then for barium hydroxide, I just want to talk about the main difference between this problem and this problem. What makes barium hydroxide so different than sodium hydroxide? Right, so our barium hydroxide has a di-basic nature. It's still strong, because it's still in our strong category, so it's still 100% going to ionize, but what does it make? So 2 times the molarity than we would normally expect. So if this ended up, when we calculated the molarity, which I have in my paper someplace, it's like 0.15 molar, how much hydroxide would I truly make? 0.3 molar, 0.30 molar, because it was going to make a 1-to-2 ratio with itself, doubling our hydroxide, which will be calculated the same way. Yeah?
If that was not a strong base, would it still dissociate with the hydroxide?
It would, and then we're going to learn how to solve for those using KBs. We'll learn how to solve those. All right, so strong stuff, honors chem. Is this a good review? We know it's strong. Okay, because that's not really part we're focusing on. So with weak bases, notice I already have showed you the dissociation equation. Water attacks the base, which this is a really generic way. We know bases are not these, right? They're usually something with an OH or like an ammonia. It's anything. But what is the job of a base? Think Bronsted definition. Its job is to accept an H plus from, in this case, water. Okay, so water is H2O. I like to write water as HOH a lot of times because if you write it as HOH, you see the 2 counterparts very easily. So this H plus is actually this one. So as this H plus gets donated to B, it makes not just HB, Hb plus, which making sure we write our ions is important because if not, it's just a wrong equation. And it leaves behind the OH that was in water as OH minus. So you're acting as a base because you're accepting NH plus, and you're making what? Hydroxide in water, which is whose definition? So Bronson Lowry talks about the accepting nature. Arrhenius is an aqueous in water. Okay, so again, we have partial neutralization or partial ionization or dissociation because it's weak, so we draw the double-headed arrow. What would be the Kb expression for this generic form? Expression. Concentration of OH minus times Hb plus, so products over concentration of the base. Why am I excluding water? Because it's a pure liquid. Same thing, products of reactants excluding the pure solids and pure liquids. Okay, so now I want you to finish the dissociation or the ionization equation here. Write the Kb expression. NH3 is ammonia. So get me started, Marcus. What are you writing?
I'm copying that from the last part.
Okay, I'll come right back to you. William, get me started. This is ammonia, so you're forming ammonium. So you're making NH4 what? Plus, because it's donating NH. Water is the acid, it's donating H plus to base ammonia. Okay, keep going, Margaret.
And it also makes hydroxide.
Okay, keep going, Miriam. Will give me the Kb expression. Concentration of ammonium. Perfect. That's it. You just have to make it act as a base. That's why this is just a little different than our acid one from yesterday. I'm going to give you a setup now for like a true problem. Give me a thumbs up when you get here. And I did print, right? Did I print this for you? So if you want to take notes on there, it might help you stay organized too. Okay, so we're doing the same situation. So we're using ammonia. I'm giving you the Kb value. Notice, oh, I just put my last paper away. Are Kb values listed on your paper? Yes or no? No? I'll show you how to find your own Kb's in a second. It's pretty simple. So here's your Kb value. It's telling you to find the pH of this molar solution. So we're going to write our equation again, just because mine's on the other slide. You might have some space under where you just wrote this. So first you write the dissociation equation, or DC. Then you're going to set up an ice. So what do I put here? 0.010. Yeah, make sure you're trying your darndest to do sig figs because your pH is based on that. So I like, some of you guys, like on your midterm, you guys wrote like 2 sig figs to remind yourself to try to stay true to that. All right, so icebox, right? I don't really know anything. I know that I want to find the pH. Well, generally for pH, what do we plug in to find pH? Concentration of what? Of H plus. Well, do we have the concentration of H plus, or will we in this scenario? No, but we'll have what? OH minus. So really, it wants us to find OH minus and just kind of backtrack. So this is like the key. So this is what we want here in the end. So how would I find that? Okay, looking for X. So I'm subtracting X here because this is dissociating, and you always have 0 and 0 of products unless otherwise noted. And then how much of these products are you making? X and X, because it's just a 1-to-1 ratio all the way across. Nobody cares about water, so just kind of scratch that out. So at the end for ice, you end up getting 0.01 molar minus X, X, and X. These values are what we plug into what? The Kb expression, which I know you can write the Kb expression, but let's just run through that one more time, because you know if you don't write it, sometimes you can mix up what you plug in. So that's the concentration of ammonia times the concentration of hydroxide over the concentration of, concentration of ammonium times concentration of hydroxide over the concentration of ammonia at equilibrium, because equilibrium expressions include equilibrium. Now, we know the Kb value to be 1.8 times 10 to the negative fifth. What I automatically want to do? Neglect x. And you need to show that to me just so I know that you know what you're doing, because some of you guys are skipping steps. So essentially, I'm only neglecting that x that's being subtracted. The others are very important because, you know, what am I solving for if I'm canceling those out? So these two products are an equal quantity, x amount times x amount, divided by what? 0.01 molar. I could put minus x and show the neglection here, but I showed it up here, so I'm good to go. This is equal to 1.8 times 10 to the negative fifth, because that was the Kb value given. So when you multiply this up, you get x squared is equal to 1.8 times 10 to the negative seventh, and x is equal to, cannot do this in my head. What is it? 4 point what? Times 10 to the negative fourth. And I get a second on that? Okay, so as we achieve x, automatically write down what the heck x means, because that's the part where we do a lot of KAs, it's just a more prevalent, type of problem. Most people will be like, oh yeah, let's say plus, let's move on. But what is x in our case? Yeah, so this is the part that we're like, okay, this is what we're finding, but we're really finding OH. So this x here is OH minus. And now that I know that, and I've written it very clearly for myself to see, I can then achieve pH pretty easily. So I like to do the modified version of pH. So how do I achieve this here? 14 minus the negative log of OH minus. Because this is POH, so 14 minus POH gives us pH. So 14 minus the negative log of 4.24 times 10 to the negative fourth. In my little video, because I watched the video I was going to have you guys watch, which was this one versus yesterday, did I tell you guys the trick for estimating with exponents? I did. Gabby says yes. I'm going to skip that part. It may have been in one or the other. So the exponent gives you the maximum the pH of the pH will be based on the ion that you have. So the POH max is 4. So it's like mid-range, so it's probably like 3.6. Can someone calculate the pH for me? 3.37. Okay, so it's in the 3s, but it's going to be between 3 and 4 because the max will be as 4, and this value tells you like how close it is to 3 or how close it is to 4. So I can estimate POH's maximum 4. So I know it's less. Like I'm going to say 3.5 just to keep it kind of general. So 14 minus 3.5 is what? 10.5. Well, this is what? 10.63. And that's something that you can do on multiple choice. If you're given enough information, you don't need a calculator, or you can estimate. But why are we including 2 decimals here? Because there's 2 sig-figs in the concentration. And let's verify that X was negligible before I move on. Let's verify that. How are you going to do that? 4.24 times 10 to the negative 4. Okay, so I'm taking X and I'm dividing it by the number I would have subtracted it from. And what's that percentage?
14.
Say again. Just okay. So yay, we can neglect because it's less than 5%. Question?
So like, I know this was in a couple of problems yesterday too. So what was like the pH of something like, since you're doing like bases, should it technically be like, should be higher?
So this is a weak base, right? So bases are going to fall between 7 and 14, but it's weak, so it's going to be closer to the 7 side, which this one is. And it's not too dilute. I mean, 0.1 would be even a higher pH than what this one is. This is a little bit more dilute, so it's a little lower. It's on the more on the 7 side. Question? No difference. It's just another way to ask, hey, this is a weak acid. How weak? This is a weak base. How weak? So if I had 1% ionization for the acid or base versus a 10% ionization for the acid or base, I would say one maybe is stronger than the other. or I would say one is more dilute than the other. So it just gives you like some context to the problem.
So if you like calculating it and you get like above 5%, you not above
Correct. Yeah, and I skipped that one on the problem set, but you basically go back to your setup with your x's involved, and it probably means you're going to do quadratic. So I would set up the quadratic and just plug in my solver. I guarantee you will not sit on the AP exam, but I don't want you to lose all your math, so I have you guys practice that. Plus, it lets you think about like when can I neglect and when can I not. Okay. All right. So let's try another KB one, but we're going to set up slightly different. Any more questions here? How do we feel? It's the same thing as KA. It's just with these. It's just with bases, I mean. All right, so morphine. Ooh, somebody had, was it morphine? You have morphine as your heroin. Oh, okay. It's close derivative. Okay. Morphine is a weak base. pH of a 0.015 molar solution of morphine is 10.19, so it's showing it's weak. Calculate the KB. So we don't know the formula for morphine, right? So I want you to set up in my general formula that I showed you initially. Try to set this up first on your own. I don't think we know the formula for morphine. It's your weird thing called. No, I'm saying I would. Guys, anytime I give you a weak base, it is going to be mono basic. It's going to have one, I wouldn't even say hydroxide, it's going to have one donation of an H+. Because actually, and let me go back to this, whose definition was so limited that it only regarded what was produced in water? Arrhenius, right? Not every base makes OHs in water. That's why Bronsted came up and was like, oh, let's expand our definition. Because morphine's actually not going to make hydroxides in water. Okay? Well, it could. Some things make, this will make hydroxides in water, but it'll make a conjugate acid, which is so awkward and weird, you don't actually know what it is. So that's why I'm going to have you write the generic B and then HB+. Because, it's sometimes not important what the formula is. It's like what it does. But still, not every base makes hydroxide. right, let's back up here so we can make sure we're on the right track. You're finishing solving complete. You're doing what you gotta do. So I just set up a generic with a B place so we don't have to worry about the morphine formula, but you will usually be given something so you can have a legitimate formula to work with. Using the initial and then the pH for the only two starting points. So in terms of utilizing the pH, what were you expected to find from that? pOH, but then that fed you OH concentration, because you actually wanted to know X. You wanted to know what this was. So one thing that's not always clear is when I find the OH, is that the initial value of OH minus, or is that the equilibrium value of OH minus? So which one should it be? The equilibrium value, because before this has occurred, before this reaction or the dissociation or ionization has occurred, we only have base. We don't have OH minus, so it can't be the initial. So once you find OH minus, that is the equilibrium concentration, which you can see the work here. pOH is 3.81, OH minus is 1.5488, which I kept out because I didn't want to have rounding error, times 10 to the negative 4th. So that's your significant amount of X that's subtracted from the reactants and added to the products. So I filled in the gaps here and here because that's a 1-to-1 ratio. But because I actually know the change, I know the dissociation, percent ionization, whatever we want to call it now, I do need to subtract that, and I get I do get a difference in value. So this is actually, is that right? Yeah, okay. So at this point, I can plug in my equilibrium values here into the KB expression, which is going to be products over reactants yet again. So products over reactants would be X times X over equilibrium value of the original base. So as you plug these values in, you should get a small value for KB. In this case, when I calculated 1.16 times 10 to the negative 6, which this is a weak base, so you know it should be small, less than 1. So that one started as analytically. Who felt like they could approach that, just putting the puzzle together? So there's not really other, there are a couple of other ways, but they're not too tricky in setting up any of these products, KAs or KBs. So I think I have one more that I wanted to attempt, and then I'll let you guys try on your own. So it's not this one. No, we're good. We're going to go ahead. Okay. So before walking you through salt hydrolysis, which I'll have about 15 minutes, and then if I don't finish today, I can do more tomorrow. I want to show you the relationship between Ka, Kb, and Kw, which I already spilled the beans a little bit, but in reference to how it works, it's related to these two equations. So take your HA here. So write this out for yourself. Take your HA, make it act as an acid. What does it make? Hydronium and A minus. Okay, so these are just generic ones. We don't have a strictly one acid we'll work with all the time. Okay, so make your base. Oh, sorry, before I move on. Write your Ka expression here. So what am I writing? Hydronium ion times A minus ion over HA. Okay. So for the other one, you'll notice I'm taking the A minus. Well, it's just because this is a weak acid. What is its counterpart here? Okay, so I'm just going to put conjugate base. It is a stronger conjugate base than the weak acid, but we'll just label it as a base. So I'm actually taking this conjugate base, I'm allowing it to act like a base. So what am I doing here? Making what? So I'm going to say make HA, which we're going to call a weak acid, but it's acting as a base, and bases always accept H pluses from water. So we're making a base. We're making A minus and H plus come together to make what? HA. There are no charges on this one because an A minus and an H plus neutralize each other, leaving behind what with water? Hydroxide. So again, we can even see the hydroxide being made, so it's acting basic. So because it's acting basic, I don't label this Ka, I label this Kb. So the K value is indicative of how the original compound is behaving as an acid or as a base. Okay, so this equilibrium expression is what? HA times OH minus over A minus. Okay, So just like in thermochem, we can, and equilibrium, we can add equations. So as I add equations, these two equations, what do I get? Remember, cancel all things that are the same on both sides. So hold on, what can cancel? The HA I here can cancel. What else? The conjugate base, A minus can cancel. Okay, what else? That's it, right? Okay, so what's remaining? 2 water, liquids yield hydronium and hydroxide. Huh, I've seen this. What is this? That's the dissociation or autoionization of water. What should the K value be for this? I mean, sorry, I said K. Did I say KB? What should the K value be for this? -14th, right? 1 times 10 to the -14th, because that is what water's dissociation expression is, or the value is. But I want to also know the expression, which I can tell you from here what the expression is. But just like in our equilibrium in the past, 2 different K expressions. When you add equations, what do you do with these? You multiply them, like we would multiply K values if we have the actual value, but we don't have the actual value. So let's take these and multiply them. So I'm going to write the first one, which was hydronium times A minus over HA. Was that the first one? Right? We're going to multiply that by the second one, which was HA times OH minus over A minus. Is that right? Okay. So as I multiply these, what do you see? Where do you see some similarities? The same things canceled that canceled earlier, yeah? So A minus and A minus, HA and HA. What do we get? Hydronium times hydroxide, which we can see that up here as well as the products. So anytime you have an acid and its conjugate base, or a base and its conjugate acid, so they have to be a pair. They can't just be like willy-nilly like apples and oranges. They got to be the same exact compound, just one H difference from itself. You have a relationship between those 2 ions with water. So what that basically means we can say is every single time we have a Ka of, like, say, acetic acid, if we take acetic acid's Ka and we multiply it by acetic acid's Kb, which is acetate ion acting as a base, we will always get Kw. So notice now I give you a whole list of Kas. It's because you can find your own Kbs. So how would I find Kb from this expression? I do Kw over Ka, and I can solve for my own Kb. Just use parentheses to your calculator, because your calculator's not really smart. Use your error. Yeah.
So, like, what does KW mean? Like, what does it represent?
It represents the relationship of hydronium and hydroxide with just the dissociation of water at a certain temperature. But it also can show us a relationship between an ion and its an acid and its counterpart, or a base and its counterpart, because acids and bases are neutralization equations. So we now know how we can find Kb's from Kas and vice versa. But you do have to make sure it's the same, like, compound with its conjugate base. It can't be 2 different things. All right, so we're going to talk about, we're using this now in salt hydrolysis. Okay, can I move on? Okay, you did your reading on salt hydrolysis, which was this nonsense. This is going to, this should have reminded you a little bit from honors chem, a little bit, but I'll show you the basics part, which is how I would explain honors chem, and then I'll show you how we would do an AP chem, which we might have to do tomorrow. So we are going to get to this, but I'm going to tell you specifically what to do shortly. So if you need to pull that, maybe put a star on reading that. So the cheap and easy way of explaining it is basically saying, okay, I have a salt. Salts are actually formed from an acid and a base. Okay, so that's what acids are. Acids and bases react in a neutralization reaction to form a salt and water. And what happens is the cation, or the anion from the acid and the cation from the base are what form that salt. That's how we form salts all the time. It's just acids and bases. So baby salt, which is made from daddy acid and mama base, are going to take on characteristics of those parents. We do say they're parent acids and parent bases. So if I have a strong acid dad and a strong base mom, what is the pH of my baby salt? Neutral. Because strong and strong fight it out, it's going to come out to be neutral overall. If I have a weak acid and a strong base that form a salt, what characteristic do you think the salt will have? So a weak acid and a strong base make a basic salt. It's going to lean towards the side that's stronger. If I have a strong acid and a weak base, acidic salt. The salt takes on the characteristic of the stronger parent. Now that is a cheap and easy way of thinking about it, but we would never write that out on AP exam. We have to write it out a little differently. So I'm going to give you an example first, and then we'll talk about the basics of it. Like the general stuff, not the basics. Okay, so we're going to use sodium acetate. How do I know it's a salt? First of all, it are two ions that come together. Okay, so it's not an acid, it's not a base, it's two ions that come together. So start off, just write down the example of sodium acetate. And in our minds, this is what we're thinking. I need to be able to predict the pH of the salt. This sodium ion and this acetate ion came from two different base and acid species. Who does sodium come from? It came from sodium hydroxide. Because you can't have a cation coming from an acid because the H plus is the cation there, so that's why you know it can't come from an acid. The acetate came from who? Acetic acid. Okay, so sodium hydroxide, acetic acid reacted to make sodium acetate and water. That's how we made this salt. This is considered a new type of base. This is strong base, and this is a weak acid. So I can already see the strong base is going to win this pH battle, and this is going to be considered a what kind of salt? A basic salt. Now, I want to know the pH of the salt when it dissolves in water, and that's the part where AP kind of comes in. We can already predict, but that just gives us like the ability to check our work. But what we would then do is say, which ion is the one that's working with water to make hydroxides? So which ion is really doing some damage here? Which one's dissociating? Which one's reacting with water? So we have two ions to pick from, and here's how you choose. Sodium ion reacts with water. What does it make? Sodium. So sodium gets with hydroxide, right? And what? H plus. Okay, so we notice this is formed immediately. What do we identify it as? Not only a base, a strong base. We're like, this thing is not going to stay as is. It's going to ionize, right? It's going to go whoop, right back to forming ion, and then the OH will grab water, or H plus is going to make water. So this is a no reaction. This one does not even happen, because as soon as it makes the product that's a strong base, it just scooches right back and reverses the reaction, not making appreciable amount of H plus. So what does acetate do with water? Acetate makes what? Acetic acid and OH minus. So we see the H gets donated to the acetate. Is this strong or weak? Weak. So does it go backwards? No, it's not going to dissociate back. So this is going to stay as is. OH is made. It's going to make an appreciable amount of OH minus, which is how we're calling this a basic solution. So it's still reversible. Before I move on though from that, the word salt, hydrolysis, what does hydrolysis or hydrolysis mean? Okay, so water is splitting something. Water is splitting up these ions and making them react, just one of them in an appreciable manner. So what I'll show you just briefly now, and then we'll do the rest tomorrow, is this is the one I will make an ice box with. Not this equation, this equation. So let's say I didn't tell you, but let's say I told you the concentration of sodium acetate was 0.1 molar. So I would have 0.1 molar, and I'd allow it to do its thing. I'd allow it to react. So I would react and subtract X and add X and add X, and I'd have 0.1 minus X and X at equilibrium. And I'd solve for X, and I would get OH concentration and move on. But here's the thing. This is acting as a what? This ion. It's acting as a base. Well, this is acting as a base because it's accepting H plus from water. So I must have a K what for it? KB. I don't have a KB for amine. I have a Ka for acetic acid. I don't have the KB for its counter ion. So how would I find the KB? Use KW. So I'd have to use KW first to find the KB, and then I would actually set up the expression and solve. The back side's exactly the same. It's just the first part you have to kind of think first before you set it. Yeah.
So is KW on
Because unless it says another temperature, we assume 25 degrees Celsius. All right, so unfortunately, you won't be able to do everything on the salt hydrolysis problem set, darn it. So what I want you to do is page 745, these questions, this is on my website, okay? A lot of this is KB, some of this is conceptual, a little bit of salt hydrolysis. But in the salt hydrolysis problem set, I'm not just straight giving you salt this time. I'm giving you some KAs, some KBs, or some acids and bases and some salt. So if you would like to start some of those, you can, because you do have the ability to do acids and bases. If you want to attempt to start, you can, but I'm going to have to do some more of that with you guys tomorrow, okay? So the salt hydrolysis problem set is 1 through 8, but we will definitely have to finish up some of that more tomorrow. It's in your packet. It says
Why don't we like to add sodium with water and ice?
sodium ion is different than sodium solid. Yeah, sodium solid is explosive with water. All right, we leave in like a minute, guys. Hey, guys.